Late afternoon sunlight stretches across the vast red landscape of Western Australia. From high above the Pilbara region,
Watch the airspeed.
the terrain appears endless. Rust-colored earth broken by low ridges, dry riverbeds, and scattered scrub. Few roads cut across the land. Few towns interrupted silence. In 1968, much of this region remains distant from the pace of modern aviation that is rapidly shrinking the rest of the world. At 19,000 feet, however, distance feels different. A four-engine turboprop aircraft moves steadily across the sky, its polished fuselage reflecting the fading light. The aircraft is a Vickers Viscount 720C, one of the most successful passenger aircraft designs of the 1950s and early 1960s. Its four turboprop engines hum with a steady rhythm, propellers spinning in precise synchronization. This particular aircraft is operating as MacRobertson Miller Airlines Flight 1750. The flight departed Perth Airport earlier that afternoon, bound north along the long western coastline toward Port Hedland, a mining town whose port exports iron ore to the growing industrial economies of Asia. For the crew and passengers aboard, the journey is routine. Regional air travel in Australia often means long distances between settlements. The aircraft serves as a lifeline connecting isolated communities to the rest of the country. Business travelers, miners, and families rely on these flights to cross hundreds of kilometers of harsh terrain that few roads traverse. Inside the cabin, the atmosphere is quiet. Passengers sit beneath the Viscount's large oval windows, watching the muted landscape drift slowly below. The turboprop engine produces a distinctive tone, lower and steadier than the raw jet aircraft. Many travelers in the 1960s consider the Viscount one of the most comfortable aircraft of its era. In the cockpit, the crew monitors the instruments with practiced familiarity. The captain and first officer sit behind a panel filled with analog gauges, engine temperatures, oil pressure, propeller synchronization, altitude, airspeed, navigation radios guiding the aircraft along its route across Western Australia. There is nothing unusual about the flight. Weather reports show clear conditions along the route. Visibility stretches for many kilometers across the desert landscape. The aircraft itself has completed thousands of hours of service. Maintenance checks have been performed according to established procedures. The routine of airline operations depends on repetition. Each flight follows the same structure: climb, cruise, descent, landing. This afternoon appears no different. The Viscount cruises steadily at altitude as the coastline disappears far to the west. Below, the land grows harsher and more remote. The Pilbara region stretches outward in a vast mosaic of red earth and dry river valleys. Eventually, the aircraft begins its descent toward Port Hedland. The crew reduces power slightly. The aircraft slowly lowers its nose, beginning a gradual descent through clear skies. The propellers continue their steady rotation as the aircraft transitions from cruise toward approach. Radio communication remains calm and routine. Air traffic control acknowledges the aircraft's progress as it approaches the destination. Estimated arrival times are confirmed. Navigation fixes are passed. Inside the cabin, passengers may begin preparing for arrival. Seat belts are fastened. Some travelers look out the windows for the first glimpse of the coastal town ahead. Others remain absorbed in newspapers or quiet conversation. The aircraft continues descending. At this stage of the flight, the aerodynamic forces acting on the wings change subtly. As altitude decreases, air density increases. Small adjustments to power and attitude keep the aircraft on a stable path. For decades, engineers have designed aircraft wings to endure enormous stresses. Every takeoff bends the wings upward under lift. Every landing reduces that stress again. Over thousands of cycles, metal structures flex and return. Most of the time, those stresses remain safely within the limits anticipated by the aircraft's designers. On this flight, however, Something inside the structure of the aircraft has already begun to change. Hidden deep within the right wing, inside a major load-bearing component of the structure, a crack has been slowly growing for months, perhaps years. It is invisible from the cockpit, invisible to passengers, invisible even to most routine inspections. The crack exists within the wing's main spar, a heavy internal beam that carries much of the aerodynamic load generated during flight. Each time the aircraft climbs, cruises, or descends, forces travel through the spar. Over time, a microscopic defect has slowly propagated under repeated stress. The metal has endured thousands of cycles of bending. Tiny fractures, too small to detect, have spread through the structure. The material that once carried enormous loads has gradually weakened. At altitude, under cruise conditions, the remaining structure has continued to hold. But as the aircraft ascends toward Port Hedland, aerodynamic forces shift again. Lift distribution across the wing changes. Stress concentrates in specific regions of the internal structure. Inside the right wing, the crack has already consumed much of the spar's strength. For a moment, nothing appears wrong. The aircraft continues its descent through clear skies. Engine instruments remain stable. The cockpit gauges show no immediate warning of structural distress. Then, suddenly, the remaining metal can no longer carry the load. Within a fraction of a second, the lower portion of the right wing's main spar fractures completely. The structural beam that supports the outer wing has failed. Almost instantly, the outer section of the right wing tears away from the aircraft. From a distance, the separation would appear abrupt and violent. One moment the aircraft intact, the next with half of its wing missing. For the aircraft itself, the effect is catastrophic. Lift vanishes on the right side. The aircraft rolls sharply as aerodynamic balance disappears. The remaining wing, engines, and fuselage are suddenly subjected to forces far beyond what they were designed to withstand. Control becomes impossible. The Viscount begins an uncontrolled descent toward the desert below. Within moments, the aircraft disappears from the sky above the Pilbara landscape. Far below, the remote terrain absorbs the impact in silence. There are no witnesses nearby, no towns close enough to see the event unfold. Only scattered debris across the red earth will later reveal what occurred in those final seconds. For investigators arriving in the days that follow, one question will dominate the inquiry. How could a modern passenger aircraft lose an entire section of its wing during a routine descent in clear weather? The answer will not be found in the cockpit. It will be hidden inside the metal itself, inside a structural component designed to last for the life of the aircraft, inside a crack that grew quietly, unnoticed, until the moment the wing could no longer hold. And when the investigation begins, engineers will discover that the failure of MacRobertson Miller Airlines Flight 1750 was not the result of a single mistake. It was a result of a chain of small decisions, design assumptions, maintenance actions, invisible fatigue inside aluminum alloy, a chain that began long before the aircraft ever left the ground that afternoon. In the decades following the Second World War, aviation transformed the geography of Australia. Distances that once required days of travel by road or rail could now be crossed in a matter of hours. For a country defined by its immense size and widely scattered settlements, the growth of regional air transport was more than convenience. It was infrastructure. Airlines connected mining towns, coastal ports, and remote communities to the major cities along the continent's edges. Nowhere was this network more important than in the vast state of Western Australia. Western Australia occupies nearly one-third of the continent, yet much of that territory consists of desert, sparse settlements, and remote resource operations. Towns along the northern coast, such as Port Hedland, grew rapidly during the 1960s as the global demand for iron ore expanded. Moving people efficiently between these distant points required reliable aircraft capable of operating from relatively simple airports. Among the airlines serving this network was MacRobertson Miller Airlines, commonly known as MMA. The airline's origins trace back to the pioneering era of Australian aviation in the 1920s and 1930s. By the 1960s, it had become one of the primary regional carriers across Western Australia, operating scheduled passenger services between the capital city of Perth and numerous remote towns scattered across the state. MMA flights were often long but routine. A typical journey from Perth to Port Hedland covered more than 1,600 kilometers of sparsely populated terrain. For passengers, the aircraft offered the most practical way to traverse this distance. For the airline, reliability was essential. Aircraft needed to withstand frequent cycles of takeoff, cruise, and landing across challenging environments. During this period, one aircraft stood out as particularly suited for regional passenger service: the Vickers Viscount. Introduced in the early 1950s by the British manufacturer Vickers Armstrongs, the Viscount became one of the world's first successful turboprop-powered passenger aircraft. Unlike earlier piston-engine airliners, turboprop engines delivered smoother performance, improved fuel efficiency, and reduced vibration. The Viscount also featured large passenger windows, a pressurized cabin, and relatively quiet operation, compared to many contemporary aircraft. By the late 1950s and early 1960s, the aircraft had earned a strong reputation for reliability. Airlines across Europe, North America, and Australia adopted the type for short and medium-range routes. MacRobertson Miller Airlines operated several variants of the aircraft, including the Vickers Viscount 720C, the specific model involved in the 1968 accident. The aircraft was powered by 4 Rolls-Royce Dart turboprop engines mounted along the wings. Each engine drove a large propeller capable of producing substantial thrust while maintaining fuel efficiency suitable for regional operations. Structurally, the Viscount reflected the engineering philosophy of the era. Aircraft designers in the 1950s relied heavily on what was known as a safe-life design approach. Components such as wings, fuselage sections, and landing gear structures were engineered with a predetermined service life. Within that life limit, the structure was expected to remain intact under normal operating stresses. The assumption was simple: if the aircraft was retired before reaching the predicted fatigue limit, structural failure would be extremely unlikely. To achieve this, engineers calculated how many cycles, takeoffs, landings, and pressurization events the aircraft could endure before fatigue might become a concern. Maintenance programs were then designed around these limits. For many aircraft of the era, this philosophy proved effective. The Viscount's wing structure, for example, incorporated a large internal beam known as the main spar. This spar extended across the wingspan and carried much of the aerodynamic load produced during flight. When an aircraft generates lift, its wings bend upward slightly. The spar resists that bending force, distributing stress across the internal structure of the wing. Each time the aircraft flies, the spar flexes, and each time the aircraft lands, the stress is released again. Over thousands of cycles, these small movements accumulate within the metal itself. Fatigue, the slow formation and growth of microscopic cracks, is an unavoidable property of structural materials under repeated stress. Engineers design around it by ensuring that the structure can endure these stresses for its intended service life. The Viscount's designers believed they had done precisely that. By the late 1960s, the aircraft had logged millions of flight hours across fleets around the world. It had established itself as a dependable workhorse for airlines serving regional routes. Yet aviation history repeatedly demonstrates a critical truth. Engineering assumptions are only as strong as the conditions under which they are tested. Aviation safety evolves through experience, sometimes through the lessons learned from accidents. On the day of the MacRobertson Miller Airline Flight 1750, the aircraft involved had already accumulated years of service. Like many regional airliners, it had operated frequent short and medium-distance flights. Each journey added another cycle of stress to the structure. Each takeoff and landing slightly flexed the wings. Nothing about this pattern was unusual. In fact, it was precisely what the aircraft had been designed to endure. Maintenance teams inspected the aircraft regularly. Scheduled servicing was performed according to the procedures established by both the manufacturer and aviation authorities. To the airline, the aircraft remained fully operational. Passengers boarding flights during the late 1960s would have had little reason to question the safety of turboprop aircraft like the Viscount. Aviation had already achieved an impressive safety record compared with earlier decades. But the conditions that ultimately produced the accident had begun long before the final flight. Somewhere within the structure of the aircraft's right wing, a minute defect had already formed. Such defects are not unusual in metal structures. Tiny imperfections in manufacturing, small scratches introduced during maintenance, or stress concentrations around fasteners can all become starting points for fatigue cracks. Normally, these cracks grow slowly enough to be detected during inspections. Occasionally, however, the combination of stress and structural geometry allows a crack to propagate in ways engineers did not fully anticipate. Inside the Viscount's wing, the main spar contained bolt holes used to secure structural components together. These openings were small but essential to the assembly of the aircraft. However, bolt holes also create stress concentration points. When a structure flexes, stress naturally accumulates around openings in the material. Engineers account for this by reinforcing those areas and controlling how components are installed. If the geometry of a bolt hole changes even slightly, the stress pattern surrounding it can change as well. Over time, these seemingly minor differences may influence how fatigue cracks begin and grow. By the late 1960s, aviation engineers were still learning how subtle variations in manufacturing and maintenance could affect long-term structural durability. The Viscount itself had already demonstrated excellent performance across thousands of flights worldwide. Yet the accident that would soon occur in Western Australia would reveal a weakness not immediately obvious during routine operations. On that December afternoon in 1968, none of this history was visible to the passengers boarding the aircraft. To them, the journey from Perth to Port Hedland was simply another flight across a vast landscape. The aircraft waiting on the tarmac appeared no different from countless others that had completed the same journey safely before. Ground crews completed their checks. Fuel tanks were filled. Cargo and luggage were loaded. Passengers boarded through the rear stays and took their seats. The turboprop engines started one by one, their distinctive whine rising into a steady mechanical rhythm. Soon afterward, the aircraft taxied toward the runway at Perth Airport. From that moment forward, the flight followed a pattern familiar to airline crews across the world. Climb, cruise, descent, yet hidden within the metal structure of the right wing, a silent process had already begun long before the engine started. A crack, microscopic at first, had been growing under repeated stress. The wing continued to perform normally. The aircraft continued to fly, and no instrument in the cockpit could reveal the damage slowly forming deep inside the spar. By the time MacRobertson Miller Airlines Flight 1750 lifted into the sky that day, the chain of events that would end the flight had already been set in motion. The aircraft itself did not yet know it. Neither did the crew. The forces of fatigue worked slowly, quietly, and without warning, until the moment the structure can no longer carry the load. Every aircraft accident is the result of multiple conditions aligning at a particular moment in time. Rarely does a single failure explain the entire event. Instead, aviation investigations often reveal a chain of influences, technical design choices, operational realities, environmental factors, and human decisions. When these elements intersect, Even a reliable aircraft can encounter circumstances that its designers never anticipated. Understanding the loss of MacRobertson Miller Airlines Flight 1750 requires examining those angles carefully. The aircraft itself, the crew operating it, the environment through which it traveled, and the systems, both mechanical and procedural, that governed its operation. Only when these elements are viewed together does the accident begin to make sense. The aircraft assigned to the flight was a Vickers Viscount 720C, a member of a family of aircraft that had already transformed commercial aviation during the 1950s. The Viscount was widely regarded as one of the most advanced passenger aircraft of its era when it entered service. It combined turboprop propulsion with a pressurized cabin, offering a level of comfort that earlier piston-powered airliners struggled to match. Powered by 4 Rolls-Royce Dart turboprop engines, the aircraft produced a distinctive sound, an even, mechanical hum that passengers quickly came to associate with reliable flight. From an engineering standpoint, the Viscount was designed with efficiency and structural strength in mind. The wings, mounted low along the fuselage, carried the engines and provided the lift required to support the aircraft during flight. Inside each wing ran a major structural component known as the main spar. This spar functioned as the backbone of the wing. During flight, enormous forces act upon the wings. Lift pulls the wings upward while the weight of engines, fuel, and the fuselage pulls downward. The spar distributes these forces across the structure, allowing the wing to flex slightly while maintaining its overall strength. Flexibility in aircraft structures is not a weakness. It is a necessity. As an aircraft flies, its wings bend upward under load. Photographs of airliners in flight often show this subtle curvature. The movement is small, but repeated thousands of times across the lifespan of the aircraft. The Viscount's designers accounted for this by constructing the spar from high-strength aluminum alloy components known as booms. These structural elements carried the majority of the bending loads generated during flight. One of these components, the lower boom of the right wing spar, would later become central to the accident investigation. Like most aircraft of its generation, the Viscount followed the safe life design philosophy. Engineers calculated the expected fatigue life of major structural components and established service limits intended to prevent structural failure during normal operations. If the aircraft was maintained properly and retired before reaching those limits, the structure should remain intact. That was the assumption. The flight crew operating the aircraft that day were experienced professionals accustomed to the demands of regional aviation in Western Australia. Flying across Western Australia required familiarity with long routes over sparsely populated terrain. Navigation aids were fewer than those available near major metropolitan areas, and alternate airports were often hundreds of kilometers away. Pilots in these operations developed a disciplined approach to routine. They relied on checklists, radio navigation, and careful monitoring of aircraft systems. Flights followed predictable patterns. Departure from Perth, cruise northward across the desert, and descent toward coastal towns such as Port Hedland. Nothing about this route suggested unusual risk. Weather conditions across the region are often clear, particularly during the dry season. The wide-open terrain provides unobstructed airspace for aircraft cruising at altitude. For the crew, the most challenging aspect of the job was often the distance itself. Long stretches of flight occurred far from major infrastructure. Yet by the late 1960s, pilots had grown accustomed to these operations. Aircraft such as the Viscount were well suited to these routes. From a flight operation standpoint, the journey was routine. There was no emergency, no unusual weather, no mechanical warnings reported by the crew before the accident. In the cockpit, the aircraft would have appeared to be operating normally. The environment, the route between Perth and Port Hedland crosses some of the most remote terrain in Australia. The Pilbara region is known for its rugged beauty, vast expanses of red earth, rocky ranges, and dry riverbeds that remain empty for hundreds of kilometers at a time. From the A, the landscape appears almost motionless. This isolation has both advantages and disadvantages for aviation. On one hand, there are few obstacles to navigation. Aircraft can cruise at altitude with little concern for terrain interference. Weather patterns in the region are often stable, especially outside the cyclone season. On the other hand, the remoteness means that emergency infrastructure is limited. If an aircraft encounters serious trouble, assistance may be hours away. Search operations can be difficult in areas where roads are scarce and the landscape stretches in every direction without clear landmarks. On the afternoon of the accident, the environment itself posed no unusual threat. Weather reports indicated clear skies and good visibility. There were no storms. No turbulence reports severe enough to threaten the aircraft structure. The environment, in this case, was largely neutral. The forces that ultimately brought down the aircraft originated not outside the aircraft, but within it, the systems. At the center of the accident was a structural issue invisible to pilots and passengers alike. Inside the wing of the aircraft, the main spar contained several bolt holes used to connect structural components together. These holes were reinforced to ensure that stress remained within safe limits during flight. However, bolt holes also represent natural points where stress can concentrate. Under repeated loading cycles, such as those experienced during thousands of flights, tiny cracks can begin forming at these locations. Normally, such cracks grow slowly. Aircraft maintenance programs are designed to detect structural damage before it reaches a dangerous level. Inspections focus on areas known to experience higher stress, including spar joints and attachment points. But the durability of these areas depends heavily on precise maintenance procedures. During earlier maintenance work on the aircraft involved in the accident, a component known as a flayed bush had been installed into a bolt hole in the wing spar. This type of bushing is intended to protect the metal structure surrounding a fastener. When properly installed, it distributes load evenly and prevents wear around the bolt hole. However, if the installation process alters the shape of the hole or introduces additional stress, the surrounding metal may behave differently under repeated loads. Investigators would later determine that the installation of this bush had subtly altered the stress distribution around the spar. The change was extremely small, far too small to cause immediate problems. But over time, repeated cycles of stress concentrated at the edge of the modified hole. Minute fatigue cracks began forming. At first, they were microscopic. With each flight, the crack extended slightly further across the spar. Metal fatigue behaves in a predictable yet dangerous way. For long periods, the crack grows slowly. The structure continues to function normally because the remaining material still carries the load. But as the crack length increases, the remaining intact metal must support more stress. Eventually, a point is reached where the remaining cross-section of metal can no longer carry the load. At that moment, failure occurs suddenly. The final fracture often happens in a fraction of a second. By the time MacRobertson Miller Airlines Flight 1750 departed Perth on that December afternoon, investigators would later discover that the fatigue crack inside the right wing spar had already consumed the majority of the structural cross-section. The aircraft had continued flying because the remaining metal still held, but its margin of safety had been quietly shrinking. Every additional flight placed stress on the weakened structure. Every climb and descent added another cycle of bending forces to the wing. When the aircraft began descending toward Port Hedland that day, those forces shifted again. Air density increased. Lift distribution changed. The weakened spar encountered stresses that exceeded what the remaining metal could endure. At that moment, the invisible chain of fatigue finally reached its conclusion. The structure that had carried thousands of safe flights was about to fail, and when it did, the consequences would unfold with extraordinary speed. The final phase of the flight began like countless others before it. High above the Pilbara region of Western Australia, the aircraft continued its descent toward the coastal mining town of Port Hedland. The sun was lowering across the horizon, casting long shadows over the desert terrain below. Inside the cockpit, the crew of MacRobertson Miller Airlines Flight 1750 followed standard descent procedures. Power settings were gradually reduced. The aircraft's nose lowered slightly, allowing the Viscount to begin a controlled descent from cruising altitude. Airspeed remained within normal limits, and the turboprop engines continued their steady rhythm. To the pilots, the aircraft appeared to be functioning exactly as expected. The aircraft itself was a Vickers Viscount 720C, a design widely respected for its reliability. Hundreds of Viscounts had accumulated millions of flight hours around the world. From the outside, nothing suggested that this flight would be different. But deep inside the structure of the right wing, the fatigue crack that had been growing over months, or possibly years, had already reached a critical stage. Investigators would later determine that the crack had progressed across most of the lower boom of the wing's main spar. Only a small section of intact metal remained. For many flights, that remaining material had continued to support the load. The aircraft had flown normally because the structural margin, though reduced, still existed. Now, as the aircraft descended through denser air, the forces acting on the wing began to change. Aerodynamic lift increases as air density rises during descent. This increased lift produces additional bending forces along the wing structure. Normally, the Viscount's wing spar would absorb these forces without difficulty, but the fatigue crack inside the right wing had already consumed most of the spar's strength. The remaining metal was carrying a load it had never been designed to bear alone. Inside the structure, stress concentrated along the thin strip of metal that still connected the spar. At some point during the descent, that final portion reached its breaking point. The fracture occurred suddenly. Metal fatigue failures rarely produce warning signs visible to the crew. There are no cockpit alarms to indicate that a spar is about to fail. No instrument displays the internal condition of a structural beam. When the remaining section of the spar fractured, the effect was immediate. The lower boom of the main spar failed completely. With that structural support gone, the outer section of the right wing could no longer remain attached to the aircraft. Within a fraction of a second, aerodynamic forces tore the outer wing section away. The separation was violent and abrupt. From the perspective of anyone observing the aircraft from a distance, the change would have been unmistakable. One moment the aircraft was intact. The next, a large portion of its wing had vanished. For the aircraft itself, the loss of the outer wing created an instant and catastrophic imbalance. Aircraft wings must produce nearly equal lift on both sides of the fuselage. When half of one wing disappears, that balance is destroyed. The left wing continued generating lift. The right side, suddenly shortened and structurally compromised, could not match it. The aircraft rolled sharply toward the damaged side. The aerodynamic forces acting on the fuselage increased dramatically. Engines mounted along the remaining sections of the wing experienced stresses far beyond normal operating limits. The pilots would have had only seconds to react. The sudden roll would have been accompanied by a violent change in attitude. Control inputs through the yoke and rudder pedals would likely have had little effect against the overwhelming aerodynamic imbalance. A modern aircraft might possess advanced flight control systems capable of detecting structural asymmetry, but the Viscount, designed in the early 1950s, relied entirely on conventional mechanical flight controls. Once the wing sections separated, the aircraft's aerodynamic stability vanished. The roll likely increased rapidly. As the aircraft banked steeply to the right, the remaining structure experienced additional stress. Fuel tanks inside the wing and engines attached to the structure added weight to the damaged side. The forces acting on the fuselage multiplied. Aerodynamic drag increased as the aircraft entered an uncontrolled descent. The pilot's options were extremely limited. With such severe structural damage, even maintaining partial control would have been nearly impossible. Within moments, the aircraft entered a rapid descent toward the desert landscape below. The Pilbara region offers few natural landmarks from altitude. From the air, the terrain appears as an endless expanse of red earth and low ridges. Far below, the ground approached quickly. Without the structural integrity of its wing, the aircraft could not recover. The descent continued unchecked. The Viscount impacted the remote terrain of Western Australia, scattering wreckage across a wide area of desert landscape. There were no survivors. Because the accident occurred in a sparsely populated region, no eyewitness accounts captured the moment of structural failure. There were no nearby towns, highways, or settlements from which observers might have seen the aircraft's final descent. The first indication that something had gone wrong came when the aircraft failed to arrive at its destination. Air traffic controllers, expecting the arrival of MacRobertson Miller Airlines Flight 1750, received no further radio communication. Attempts to contact the aircraft produced no response. Gradually, the realization spread through airline operations and aviation authorities. The aircraft had disappeared. Search operations soon began across the vast Pilbara region. Aircraft and ground teams scanned the desert landscape, searching for any sign of the missing Viscount. Eventually, wreckage was located scattered across the red terrain. Even before investigators arrived at the crash site, the distribution of debris suggested a critical clue. Large portions of the right wing were found separated from the main wreckage field. This pattern indicated that the wing had detached before the aircraft struck the ground. For investigators trained in accident reconstruction, this observation immediately narrowed the possibilities. The accident had not begun with engine failure. It had not begun with pilot disorientation or weather conditions. Instead, something had caused the structure of the aircraft itself to fail in flight. The mystery now shifted from the cockpit to the aircraft's internal structure. Somewhere within the metal framework of the wing, investigators suspected the chain of failure had begun. Understanding exactly how that failure occurred would require meticulous examination of the wreckage. In the coming weeks, engineers and accident investigators would analyze fractured metal, damaged components, and structural remnants recovered from the desert. Their findings would reveal a story that had been developing quietly inside the wing for years. A crack so small, it once measured only fractions of a millimeter. A defect invisible to the crew and passengers. A structural weakness that slowly expanded with each flight until the moment the spar could no longer carry the load. The accident sequence itself had unfolded in seconds, but the process that caused it had taken much longer. And uncovering that process would become the focus of the investigation that followed. When an aircraft disappears in a remote region, the first challenge is simply finding it. The Pilbara landscape of Western Australia stretches for hundreds of kilometers in every direction. Sparse vegetation, rocky ridges, and red earth make aerial searches difficult, especially when debris is scattered across wide areas. After MacRobertson Miller Airlines Flight 1750 failed to arrive at Port Hedland, aviation authorities began coordinating search operations across the region. Aircraft from nearby bases joined the effort, flying low over the desert in expanding search patterns. Ground teams prepared to move into remote areas if any signs of wreckage were spotted. Eventually, the search crews located debris scattered across the red terrain. From the air, the distribution of wreckage immediately suggested that the aircraft had broken apart before reaching the ground. Large components were spread across a broad area, rather than concentrated at a single impact point. This pattern provided investigators with an early clue. The accident had likely involved an in-flight structural failure. Soon afterward, teams from Australia's Aviation Authority arrived to begin a detailed investigation. Their work will be overseen by the Department of Civil Aviation, which at the time held responsibility for accident investigations. The first stage of the investigation focused on documentation. Investigators reviewed maintenance records from MacRobertson Miller Airlines, examining the aircraft service history. They analyzed flight logs, inspection schedules, and any reported mechanical issues prior to the accident. Nothing immediately suggested a catastrophic mechanical failure. The aircraft had been maintained according to standard procedures. Scheduled inspections had been completed. There were no reports of unusual structural damage during recent servicing. Yet the physical evidence scattered across the Pilbara told a different story. As wreckage pieces were catalogued and recovered, investigators began reconstructing the aircraft's final moments. One of the most important discoveries involved the right wing. Large portions of the outer right wing were found separated from the main wreckage area. This confirmed that the wing section had detached before the aircraft struck the ground. Investigators transported key structural components to laboratories for closer examination. There, engineers began studying the fractured metal surfaces of the wing's main spar. In structural failure investigations, the surface of a fracture often tells a detailed story about how the break occurred. Fatigue cracks produce distinctive patterns that differ from sudden overload fractures. When engineers examined the broken spar components from the right wing, they observed exactly such patterns. The fracture surface revealed a large fatigue crack that had propagated gradually through the metal. Using microscopic analysis, investigators determined that the crack had grown across approximately 85% of the spar's cross-section before the final fracture occurred. This meant that only a small portion of intact metal had been supporting the load during the aircraft's final flights. The discovery immediately raised another question. How had such a large crack remained undetected? To answer that question, investigators focused on the origin of the crack. At one specific point along the spar, engineers identified the location where the fatigue fracture had begun. The crack had originated at the edge of a bolt hole used to attach structural components within the wing. Bolt holes are common features in aircraft structures, but they are also areas where stress can concentrate. Under repeated loading cycles, these locations require careful engineering and maintenance to ensure that fatigue does not develop prematurely. Closer examination revealed another critical detail. Installed within the bolt hole was a flayed bush, a small cylindrical component designed to protect the surrounding metal from wear and distribute mechanical loads more evenly. When properly installed, such bushings help extend the life of structural joints. However, investigators determined that the installation of this particular bush had subtly altered the geometry of the bolt hole. The change was extremely small, far too minor to cause immediate structural problems, but it had an unintended consequence. The altered shape of the hole created a stress concentration point within the spar. Over time, repeated cycles of bending stress during flight began to initiate microscopic cracks along the edge of the hole. Each flight added another cycle of stress. Each cycle allowed the crack to grow slightly larger. The process was slow and invisible. Routine inspections at the time were not designed to detect fatigue cracks of such small size within that specific location of the wing structure. By the time the crack reached a detectable size, it had already propagated through a significant portion of the spar. Eventually, the crack extended across most of the structural cross-section. When MacRobertson Miller Airlines Flight 1750 began its descent toward Port Hedland on that December day in 1968, the spar was already critically weakened. Only a narrow strip of metal remained intact. The descent through denser air increased aerodynamic forces on the wing, producing bending loads that exceeded what the remaining material could support. The final fracture occurred suddenly. Once the lower boom of the spar failed completely, the outer wing section detached, leading immediately to loss of control. The investigation now had a clear explanation for the accident, but understanding the cause raised deeper questions about aircraft design philosophy. At the time, many aircraft, including the Vickers Viscount, relied on the safe life design principle. Engineers calculated how long a structure could safely endure repeated stress cycles and then set retirement limits for the aircraft. However, the safe life approach assumes that the structure remains free of unexpected defects. The accident demonstrated that even a small maintenance-induced change could significantly alter fatigue behavior. As the investigation progressed, aviation authorities recognized that this issue extended beyond a single aircraft. If similar structural conditions existed elsewhere in the Viscount fleet, other aircraft might also face the risk of fatigue cracking in critical components. In response, regulators ordered additional inspections of Viscount aircraft operated in Australia. Airlines were instructed to examine wing spar structures more closely, particularly around bolt holes and bush installations. Some aircraft underwent structural modifications or had their service life limits reduced. International aviation authorities also reviewed the findings. The accident contributed to a broader shift in how engineers approach structural fatigue in aircraft design. Rather than relying solely on safe life calculations, engineers increasingly adopted fail-safe and damage-tolerant design philosophies. These approaches assume that small cracks may occur during the life of the aircraft. Instead of preventing cracks entirely, structures are designed so that damage can be detected and repaired before it leads to catastrophic failure. Improved inspection techniques, including non-destructive testing methods, were gradually introduced across the industry. These methods allowed maintenance crews to detect fatigue cracks that would previously have remained hidden inside structural components. In aviation, accidents rarely end with the crash itself. The true impact unfolds afterward, inside engineering offices, maintenance hangars, regulatory agencies, and training programs across the world. Each investigation adds another layer to the collective understanding of how aircraft behave under stress, how systems fail, and how safety can be strengthened. The loss of MacRobertson Miller Airlines Flight 1750 was no exception. What began as a sudden structural failure over the remote Pilbara landscape ultimately reshaped how engineers and regulators thought about fatigue within aircraft structures. The aircraft involved in the accident, a Vickers Viscount, had been considered one of the most reliable airliners of its generation. By the late 1960s, Viscounts had accumulated millions of flight hours in service with airlines across Europe, North America, Africa, and Australia. Yet the investigation demonstrated that even a proven aircraft could experience unexpected vulnerabilities. The fatigue crack discovered within the right wing spar had developed slowly over many flight cycles. For a long period, the crack remained small enough that the structure continued to perform normally. But once the crack grew large enough, the remaining metal could no longer carry the aerodynamic loads imposed during descent. The result was instantaneous structural failure. For aviation engineers, the most important lesson was not simply that fatigue cracks could form. That was already well understood. The deeper lesson was that unexpected structural conditions could significantly shorten the fatigue life predicted during aircraft design. In this case, the installation of a flayed bush within a bolt hole, an apparently minor maintenance action, had altered the stress distribution in the spar. The change was subtle, so subtle that it remained undetected during routine inspections. Yet over thousands of flight cycles, the altered stress pattern accelerated the formation of a fatigue crack in one of the most critical structural components of the aircraft. The accident forced engineers to confront an uncomfortable reality. Aircraft structures do not always behave exactly as theoretical models predict. Real-world conditions, maintenance practices, small manufacturing variations, and environmental factors can influence how fatigue develops over time. In response, aviation authorities in Australia initiated a series of safety measures following the accident. The Department of Civil Aviation issued directives requiring additional inspections of wing spar structures on Viscount aircraft operating within the country. Airlines were instructed to carefully examine bolt hole areas and structural joints where fatigue cracks might originate. Maintenance procedures were also reviewed. Technicians received updated guidance regarding the installation of bushings and fasteners in critical structural components. Even small deviations from design specifications were now recognized as potential contributors to long-term fatigue damage. At the same time, the accident contributed to a broader shift in aviation engineering philosophy. During the early decades of commercial aviation, many aircraft were designed under the safe life principle. Engineers calculated how long a component could endure repeated stresses and then required that it be retired before reaching that limit. However, accidents like the one involving MacRobertson Miller Airlines Flight 1750 demonstrated that unexpected flaws could undermine these predictions. If a hidden crack existed within a structure, the remaining life of that component might be far shorter than engineers had anticipated. Gradually, aircraft designers began adopting more advanced structural philosophies. One of these approaches became known as damage-tolerant design. Rather than assuming that structures would remain completely free of cracks, engineers began designing aircraft so that small cracks could exist without immediately leading to catastrophic failure. This philosophy required multiple layers of structural redundancy and inspection. If a crack formed in one part of the structure, other components could still carry the load long enough for the damage to be detected and repaired. At the same time, advances in non-destructive inspection techniques made it possible to detect fatigue cracks earlier. Methods such as ultrasonic testing, eddy current inspection, and radiographic imaging allowed maintenance crews to examine structural components without dismantling large portions of the aircraft. These technologies were gradually integrated into maintenance programs across the aviation industry. The accident in Western Australia became one of many case studies demonstrating why these improvements were necessary. Today, modern airliners are designed with far greater awareness of fatigue behavior. Engineers now assume that microscopic cracks may form during the life of an aircraft. Structures are designed so that these cracks grow slowly and remain detectable long before they threaten the integrity of the aircraft. Maintenance programs include detailed inspection schedules targeting specific structural locations known to experience high stress. Each of these practices emerged through decades of experience, sometimes through difficult lessons learned from accidents. The loss of MacRobertson Miller Airlines Flight 1750 added another chapter to that history. Far from the busy airports of major cities, the Pilbara Desert eventually returned to its quiet routine. Wind moved across the red earth. Seasonal rains carved temporary rivers through the rocky landscape. The remote terrain where the aircraft fell remained largely unchanged. But within the world of aviation engineering, the event left a lasting mark. Design assumptions were questioned. Inspection methods were strengthened. Maintenance procedures were refined. The goal of these changes was simple: ensure that hidden fatigue cracks could never again progress unnoticed to the point of catastrophic failure. Aviation safety evolves gradually. Every improvement, every procedure, and every inspection standard carries the influence of past experience. The story of MacRobertson Miller Airlines Flight 1750 is therefore not only the story of a structural failure, it is also the story of how aviation continues to learn from its past. Quietly, methodically, and always with the intention that the lessons written into aluminum and steel will make future flights safer than those that came before.